as a product manager here at Aliro Quantum, I work on different products, and one of ours is a quantum network simulator. So I understand exactly the difficulty and level of detail that you need to be able to realistically simulate these networks. And also, as a product manager, I care about it being useful, not just technically correct. So I know exactly the kinds of problems that people run into that require simulation as the solution. So throughout this webinar, we've been talking a lot about how it's very similar to our previous encryption sort of styles in that it's easy to integrate with your network. It's easy to get the keys passed up to your same encryptors and use things in the same way. And all of that is true. But what we've been emphasizing a little bit less is how what we're doing on a physical level is very different from what's happening in the classical setting. And because of that, there's a lot more complexity that needs to be managed in how you run it, but also in how you design it and making sure that things will work correctly, because there's a lot more that can go wrong, which is perfect domain for simulations. Any industry where there's a lot that can go wrong is an industry with a lot of simulations going on. So when we think about classical networking, we tend to be sending a lot of photons for a 1 and still a lot, but less photons for a 0. So you can think of it, the optical fiber, as like a cable, or think of it as like a hose that we're spraying a ton of water through. So we got like pressure washer setting for 1 and just like hose setting for 0. Whereas in quantum networking, depending on the encryption or depending on the encoding, that we're using, we might have our qubit, our entangled bit that we're sending to Alice and Bob be a single photon, so a single piece of light, which is so tiny and so delicate. And there's only one. You can think of it as like a delicate little marble going down your hose. So you can see where, very different from the spraying water setting, there's a lot that can go wrong. If another little piece of light gets into the optical fiber, then it's destroyed, maybe because if they're too close together or too similar, you won't be able to get the information from your actual photon that you care about. Maybe your one little photon goes missing because of loss along the channel. There's so many different things that can go wrong, even beyond adding or losing photons. You can get your photon from A to B, but maybe it gets a little mussed up along the way. Its state is different when it arrives than it was when it was sent, and we need to be able to compensate for that to make sure that it arrives in the condition that, or at least we can work our way back to figuring out what the condition was when it was sent. So there's a lot of details that we can simulate to figure out, with a certain set of equipment, is it possible to get the kind of performance that you're looking for over a certain distance in certain conditions. So it matters whether your fibers are buried deep underground. It matters how they're shielded. It matters how close they are to other optical fibers and what kinds of signals are being carried on those other optical fibers. Is it more quantum networking? Is it a super high bandwidth channel that's carrying classical communication? What's going on there? It matters if the fiber is strung up high in the air and it's being tossed around in the wind and the sun is shining on it. Temperature changes matter, especially when they go from hot to cold quickly. That can change the length of the fibers, and we need to be taking that into account because we're timing very precisely how long it takes for these individual entangled photons to get from the source to the detector, so that we know which key pair this should be a part of, which other photon on the other side, which might have a different length of link. So there's so many details here that there's a lot that could go wrong. And by simulating, we mitigate that risk. So we can say, what if we had this individual hardware component talking to this one, and we had these kinds of fibers in this kind of environment, and we ran it for this long, what would happen? And in doing that, we're able to de-risk deployments so that when you actually buy the hardware and put it out there, you have a pretty good idea of how it's going to function. It also lets us do an iterative process where we see how the simulation is saying something's going to work, and then maybe we update the design accordingly to factor in for certain problems before they arise. Or maybe we deploy the network and we compare it to the simulation and we see that something is off. And instead of just accepting that as, oh, well, it is what it is, because we have the simulation, we can say something is different here. And it helps us work backwards and sort of debug the physical network to figure out what the unexpected problem is. which is very powerful in getting excellent performance out of these networks. For this second question about what aspects can be reliably simulated, I'm going to pass it off to Suparna.
Thanks, Cara. Those are great points. We do have to consider that theory can only take us so far, so simulations are absolutely important. And in the case of BBM 92 protocol, a lot of the core aspects, in fact, all of them, can be reliably simulated. They follow the logical flow of the protocol, and these like entanglement distribution, random basis selection, qubit measurements, calculation of QBER, all of these can be reliably simulated. And simulation tools can also help with modeling non-ideal scenarios like Cara was talking about. So errors, basis mismatches, eavesdropping strategies, all of these. Regarding what aspects require physical implementation to understand fully, although these simulations can provide us great models, we need to be accurately and realistically simulating them. And in order to do that, a number of physical parameters must be drawn from actual hardware and experimental setups. So this would either entail partly or largely realizing that physical implementation. For example, dark counts in detectors, channel losses, and sources of noise. These vary depending on the environmental conditions, like Cara was talking about temperature, background light, and all of these comes into picture. So these values are sometimes difficult to predict or approximate purely through simulation, and they often need to be derived from characterizing the experiment. And more importantly, I also want to touch upon this aspect, which is when we try to perfectly model certain types of sources of error, such as, for example, modeling strong polarization dispersion in long fibers and incorporating this along with modeling loss in the fibers, and say we are also going beyond BBM 92 and considering multiple entangled parties that are shared between multiple different end nodes. In all of these scenarios, the state space, it grows exponentially. So we know that it grows exponentially with number of entangled parties. And in addition, for some of these errors, in order to model them, we have to consider so many more optical modes being present, such as for dispersion and incorporating loss into it, that the state space grows exponentially in the sense that the density matrix and the global quantum state for this density matrix, it becomes very large and very hard to store and manipulate. So this is where we have a quote that's famously also said by Richard Feynman, that nature is not classical. So you need to be using quantum simulators to simulate it eventually if you want a lot of realism and a lot of scaling in order to be possible. So simulations are a great tool. We can really use them to our benefit to simulate a lot of different aspects of both BBM 92 and even other protocols. For realistic systems, we have to keep in mind and benchmark what are capabilities in terms of state space and storage and manipulation of large density matrices when we are dealing with this.